Hello, my name is Jathin, and today I'm going to be making, I'm going to be reading through a PPT made by Ronald A.Fisher, and I'm going to be speaking about his contributions and the life he's lived. Ronald A.Fisher, the father of modern statistics, he was a pioneer in statistical theory and experimental design. This PPT is made by me, Ayush, me, Srijan, and Aadvik. This is a picture of Ronald A.Fisher when he was in horror school. Introduction. Creating a PowerPoint presentation on a Fisher serves the purpose of illuminating the extraordinary contribution of this influential statistician and geneticist. Ronald A. Fisher, a towering figure in the field of stats, has left an indelible mark on scientific research and experiment. He basically uh, developed a lot of things which we use in everyday life and which makes our life even more easier than already it is. This presentation aims to delve into Fisher's life, his groundbreaking statistical methodologies, and his profound impact on scientific community. As a pioneer in the early 20th century, Fisher revolutionized the way researchers approach statistical analysis, introducing concepts like analysis of variance, experimental design principles, and maximum likelihood estimation. By exploring these concepts in a visual format, the presentation seeks to make Fisher idea more easier and easier to understand and more eye-catching to the normal audience. Ronald A. Fisher's full name was Sir Ronald Aylmer Fisher, was a prominent British statistician, evolutionary biologist, and geneticist. He was born on 17th February 1980 in London, England, and he passed away on 29th July 1962 in Adelaide, Australia. Sir Ronald A. Fisher was not only a statistician, he was a mathematician, a biologist, and a lot of other things. And he's not only contributed to one field, but he's contributed several other fields, which makes him a very respected person among the community. Fisher made significant contributions to several fields, including stats, genetics, evolutionary biology. Here are some key aspects of the early life and education background. Education. Fisher attended Harrow School, a prestigious independent school in London, where he started showing early, early liking for mathematics, early promises that he's going to start liking mathematics. He later studied in Cornwall and Cag's College, Cambridge, where he focused on mathematics. Here it goes to show that he already knew that mathematics is what he wanted to do in his entire life. Taking a mathematics when he was in school as well as in college proves that he had a profound love for mathematics. Fisher married Ellen Guinness in 1917, and they had two daughters. Despite facing health challenges, Fisher contributed significantly to scientific research. He was opposed and he was threatened by many people because of his research, but he still continued to do his research and he pushed all of the material out on to for people to read. And he didn't give he didn't care about anyone else because he really wanted to put out his idea in front of many people and revolutionize his idea. Here are some of his contributions: analysis of variance, ANOVA, design of experiments, Fisher's randomization test, maximum likelihood estimation, Fisher's information, multivariate statistics. The first one in the entire contribution he's done is ANOVA. In ANOVA, the basic idea is to partition the total variability observed in the set of data into different components, namely the variability between groups and the variability between groups. The partitioning allows researchers to access whether the observed differences between groups are likely true differences or due to some random sampling. Uh, Fisher's ANOVA includes calculating F statistics, which is the ratio of the variance between groups to variance within groups. If the variance between groups is significantly larger than the ratio within groups, it goes to show that it's a rejection of the null hypothesis. which posits that there are no significant differences between the groups. ANOVA is widely used in various fields, including experimental psychology, biology, and industry, to compare means in experiments with more than two conditions or groups. It provides a robust statistical framework to make inferences about population mean based on sample data. Here, basically, it tells us that ANOVA helps us to identify whether the groups are interlinked or not, and if they are not interlinked, and how to find out what type of difference, what type of links do they have in between them. ANOVA is designed to access whether there are statistically significant differences between the mean of two or three or more independent groups. It helps to determine if observed differences among the mean are due to genuine differences in population means, or if they could attend attributed to something named as random sampling. And our components are broken down into mainly four major components. The first one is between group variability, which means variation attributed to differences between the group means. Within group variability, variation with each group. Post HOC test. If ANOVA indicates that there are no significant differences among group means, post HOC test can be conducted to identify which specific group differ from each other. With basis to tell us that if 10 groups are given in a variability test, which of the groups are connected to each other can be identified by a basic HOC test. And some of them are Hershey's constant significant difference, HSD, or bonfire correction, and others. Experimental design was a pioneer or a very important played a very important part in Fisher's life. Fisher basically explained that experimental design should be used to analyze all the stats, which basically helps us put stats into a very statistical data into a very clean and organized manner, into a more eye-pleasing manner, and it should be used for everything. Uh, Fisher's work in experimental design was closely tied to development of ANOVA. He emphasized the importance of carefully designing experiments to maximize the efficiency of statistical analysis and the validity of conclusions drawn from the data. This is all. Thank you.
Now I'm going to talk about Fisherian randomization test. Under this comes contingency table, which cross-tabulates the two categorical variables. The table has rows and columns which represent categories of each of the variable. The cells contain the frequencies or counts of observations falling into each combination of categories. The Fisherian randomization test is commonly used to access the independence of two categorical variables. The hypothesis shows null. It states that there is no association between the variables, while the alternative suggests a significant association. Its key innovation is randomization. It is used to generate a distribution of possible tables that could have resulted under the assumption of independence. The test statistic used in Fisher's exact test is based on the hypergeometric distribution. It measures the probability of observing a distribution of frequencies in the contingency table. The p-value is the probability of obtaining a result as extreme as or more extreme than the observed result, assuming the null hypothesis is true. A small p-value suggests evidence against the null hypothesis, indicating a significant association between the variables. Some researchers compare the calculated p-value to a predefined significance level, often 0.05. If the p-value is less than or equal to the significance level, the null hypothesis is rejected in favor of the alternative hypothesis, suggesting a significant association between the variables. In the early 20th century, Fisher introduced the principles of experimental design as a systematic approach to planning and conducting experiments. In his groundbreaking book, The Design of Experiments, the key concepts in this book include randomization, which involves in randomly assigning experimental units to different treatment groups. He also talked about replication, which involves conducting multiple experimental runs to obtain more reliable estimates to treatment and effects variability. He talked about blocking, which is a grouping of experimental units with similar characteristics to reduce variability and enhance the precision of estimates. He contributed to the development of Latin square designs, which are useful for controlling variation by arranging experimental treatments in a square grid, ensuring each treatment appears once in each row and column. He stressed about the importance of practicality in experimental design, aiming for efficiency without sacrificing the scientific rigor. Designs should be both statistically sound and feasible in real-world applications. Fisher also emphasized the importance of likelihood in statistics. Likelihood is a measure of how well the model explains the observed data. His work also contributed to the use of log likelihood function. Instead of only likelihood function, the logarithmic simplifies calculation and does not change the location of the maximum likelihood estimates or MLE. MLE involves finding the values of parameters that maximize the likelihood function. Mathematically, Fisher introduced the concept of Fisher information, which measures how much information the observed data can carry about the parameters. The Fisher information matrix is crucial in understanding the sampling variability of MLE. Fisher's works, combined with subsequent developments, showed that under certain conditions, the maximum likelihood estimates have desirable asymptotic properties such as efficiency and normality.
Fisher information. Precision of estimators. The Fisher information is related to the precision of maximum likelihood estimators, also known as MLEs. Larger values of Fisher information indicate greater precision in estimating the unknown parameters. Kramer-Rao inequality. The Kramer-Rao inequality states that the variance of any unbiased estimators for a parameter is greater than or equal to the reciprocal of the Fisher information. In other words, no unbiased estimators can have a smaller variance than the inverse of the Fisher information. Now we're going to speak of efficiency of estimators. Efficient estimators are those that achieve the Kramer-Rao lower bound, meaning they have the smallest possible variance among unbiased estimators. MLEs are asymptotically efficient, meaning that the sample size increases, their variance approaches the Kramer-Rao bound. Additivity property. If you have any independent and identical distributed observation, the Fisher information for the entire sample is the sum of Fisher information for each observation. Connection to standard error. The square root of the inverse of the Fisher information provides an estimate of the standard error for the maximum likelihood estimator. This is a measure of the uncertainty and variability associated with the parameter estimate. The Fisher information is defined as expected value of negative second derivative of a log likelihood function with respect to the parameter theta. Mathematically, it is expressed as I theta equals E into minus d square by d theta square log L theta. Here L theta is the likelihood function and d square by d theta square represents the second derivative with respect to theta. Multivariate statistics. Multivariate statistics involves analysis of data sets with more than one variable. This field encompasses a wide range of techniques for understanding relationships and pattern among multiple variables simultaneously. Some of the key concepts and techniques associated with multivariate statistics that build upon Fisher's contribution include uh, MANOVA, meaning multivariate analysis of variance. MANOVA extends Fisher's analysis of variance to situations where there are multiple dependent variables. It is used to test the hypothesis that means several groups are equal across multiple variables. Multivariate regression. Building on linear regression, multivariate regression considers the relationship between multiple independent variables and one or more dependent variables. This allows for a more comprehensive understanding of the factors influencing an outcome. Principal component analysis, also known as PCA. PCA is a technique that transforms the original variables into a new set of uncorrelated variables called principal component. It is used for dimensionality reduction and identifying patterns of variability in high dimensional data. Canonical correlation analysis (CCA). CCA examines the relationship between two sets of variables, seeking linear combination that maximizes the correlation between the sets. It is often used when there are multiple dependent and independent variable sets. Discriminant analysis. Discriminant analysis involves classifying observation into predefined groups based on their characteristics. Fisher's linear discriminant analysis (LDA) is a specific technique within this framework that seeks to find a linear combination of features that best separates different groups. Factor analysis. Factor analysis, the underlying structure of observed variable identifying common factors that explain the correlation among them. It is used to reduce data complexity and identify latent constructs. Conclusion. Ronald A. Fisher's impact on the field of statistics is immeasurable. From his groundbreaking work in experimental design to the development of statistical techniques like ANOVA and maximum likelihood estimation, Fisher's intellectual legacy has shaped the way we analyze data and draw meaningful conclusions. Fisher was not merely a statistician, he was a pioneer in statistical thinking. His emphasis on rigorous experimental design, the analysis of variance, and the likelihood laid the foundation for modern statistical methodology. Like any influential figure, Fisher faced challenges and controversies. However, it is essential to view his work in the context of his time, recognizing that his innovative thinking paved the way for the evolution of statistical theory.